Okay. Today we'll talk about chapter 9, calculus of variation. So what does this chapter consist of? Here in this chapter, you're going to use some new methods to obtain differential and differential equations and transfer functions. That has an application in signals, you can say signals and control systems, but that's not our main objective here. Here you can solve the problems that you used in Physics 1 in Newton's method. You can solve them here in a new method called Euler Lagrange. Okay, Euler Lagrange is the combination of two scientists' methods using a certain function called the mechanical module. This is the function that we're going to use, partial x dot d dt minus partial x equals to f. Okay, this is our main function that we're going to use. Okay, so we know we need to introduce some constants that we used before, like I, which is moment of inertia, m, which is mass, r, which is radius, L, which is the length of a rope. Okay, I think that these are only the constants that we're going to deal with in this chapter, probably. There are some, and there's G actually, the gravitational acceleration. Anyway, so we need to introduce some of our kinetic and potential energy equations. PE, or which is V, you can say it's V, the same thing. We have some equations that we need to understand first. The first equation, which is mgx. If you have an object that is elevated or has change in height in x, and this object weighs m, okay, the potential energy of this object is mgx. Okay, as you see here that we're going to use the variable x for distance. Vertical or horizontal, doesn't matter, we're going to use the variable x. If you have both directions, like 2D change, you can use x1 and x2. We're not going to use y. All right, that's the first thing. Now there's another equation for potential energy, which is for spring. An object that is tied to a spring. Okay, and this object weighs m. The potential energy of this object is half k spring constant x square. Okay. Now, as for kinetic energy, we're going to have some equations that you already studied before in dynamics. The first equation is for an object that has a change in place that's to the respect of a velocity. Like it has a velocity, and this object changed according to this velocity. The equation of this change is the famous kinetic energy equation, which is half mv square, or in our case, since we're only using the variable x, v is basically the differentiation of time of displacement dx over dt is equal to v. In other description that we're going to use, it's x dot. Dot means the derivation to the respect of time. Okay, it's not dash, it's not the same of dash. Dash is just differentiation to respect of a variable. But the prime here, it means a prime, or you can say dot or whatever. It means it's differentiation to the respect of time. Okay, so represented here, we'll get half mx dot square. Okay, that's for change or change in direction, velocity, whatever. We'll use this equation, velocity, and here for elevation, and here for spring. for a spring. Okay. What else we have? We have the kinetic energy of a rotating object. Okay. We will keep this for the end. Okay. We'll keep this for the end of, or you can say the other part of the tutorial. Okay, let's have an application of what we obtained here. Let's say, let's go to the next problem. Okay, let's say that we have this system. This is a falling ball in a free fall. Okay, just simple free fall. Okay, we don't have any exerted forces, anything but the gravitational acceleration. So we will use the equation that you learned before. Let's say that I want to find the KE first, the summation of kinetic energy formulas. Just look at the object here. The first thing you need to obtain, is there any rotation? Again, we are not going to cover rotation in this tutorial. We covered in the next tutorial or at the end of this tutorial. Anyway, if there's rotation, there isn't. Okay, what do we have here? We have a change in height. Okay, there's change in height. Okay, what do you have other than change in height? You can see that there's a velocity. Okay, there is a velocity. So velocity. So what do you see here? That you have these three informations that you obtain just by looking at the system and reading the question and checking if there is any needed information that you need to apply to this equation. Okay, so as for the kinetic energy, we will use half m x dot square. Okay, we don't have any rotation, so we're not going to have any other formula but this, or any other equation but this. Now, as the summation for potential energy, we don't have a spring. All right, so we don't have a spring here, but we have a free fall, or you can say change in height or elevation. The equation of change of elevations, again, negative mgx. I think that I wrote the mgx in the first slide. It's negative mgx. Please correct that in your notes. Okay. Now, as for the Lagrangian, the Lagrangian is basically the kinetic energy minus the potential energy. So you'll get half mx dot square minus, which is plus mgx. Okay, now you need to apply the mechanical module, the first equation that I wrote in the tutorial. So which is the following: partial L over partial x dot d dt minus partial L over partial x equals to F. Okay. Let's first apply partial L over partial x. We will get mg. All right. And we have partial L over partial x dot. It's going to be, see here, looking by this, x dot is our variable. Okay. X dot is a whole variable, not x. It's x dot, the full variable. So we need to find the derivation of this. It's basically, if you have, let's say, if you have y squared and I told you to find the derivation, which is going to be 2y, right? That's it. So it's the same thing here. So the derivation of half mx dot square, bring the 2 down and minus 1 here, you will get mx dot. Okay. Now we need to find the d dt, which is the derivation to the respective time. Now we're using a different type of differentiation. It's not the same as the first one. So d dt of this mx dot, it's going to be mx double dot. M is just a constant, so you cannot derive it. You can't do anything with it. It's just a constant, like any number, 5, 6, 700, whatever. Okay, now we need to apply this, the mechanical module. F is equal to ddt partial L over partial X dot, which is this term. So it's mx double dot minus here, minus partial L over partial X, which is mg. Okay. You can see here that this is our mechanical module. Okay. Since we're dealing with conservative forces, this means that this is equal to 0. See, you need to understand this topic. I'm not sure if it's going to be in your midterm, but just understand it for your information. So if you're having conservative forces, the summation, or you can say F, is going to be equal to 0, which will give you this following expression, mx dot equals mg, because equal to 0, we took this to the other side, etc. Okay? You can see here that we can cancel the m's and you'll get x dot is equal to g, which is equal to 9.81 meter per second square. So what you understood from this, or what you obtained from this method, that the acceleration of the falling object is equal to g, which is 9.81 meter per second square. Okay, you can see that this is, you can say it's a bit difficult for nothing, that you can use Newton's method, but you'll appreciate this method in future applications, especially if you're planning to specialize in physics and quantum mechanics. This is the introduction of this major, you can say. Anyway, so let's do the same thing here. I want to do something different. I said I want to keep the rotation for the last, so let's keep it for the last. Let's go to the spring problem. Okay, we have a spring. Look at the whole system. Do you have any rotation? There's no rotation. Okay, what do you have here? You have a change of height? No, there's no change of height, no elevation. There's no elevation. Okay. What do we have here? We have a spring. Okay. And we have a velocity, acting velocity. Okay. So based on this information that you found, you need to obtain a differential equation or a mechanical module. Then you can obtain a differential equation or whatever you want. Okay, so let's start. We need to write our kinetic and potential energy equations. So the kinetic energy in this problem, by looking here and obtaining these values or these properties, you can see that we have a velocity. Spring is just a potential energy, so we'll use it in the second part or the second equation. So the velocity, the equation of velocity is equal to half mx dot square. Please remember this. Okay. As for the potential energies, we don't have an elevation. Okay. We only have a spring. So the spring has its own potential energy equation, which is equal to half kx square. Okay, now apply the Lagrangian equation, which is kinetic energy minus the potential. So you get half mx dot square minus half kx square. Okay, let's find the mechanical module here. You need partial L over partial x first, which is, by looking here that we don't have an x here, we have only an x dot, so we don't need it. We need here, we need to look here. So you can see, you can derive this term. You will get half kx. As for d dt, partial L, partial x dot. First work on this, then apply d dt. Okay, so by looking here, you can derive this. Again, as I said, you need to use this as a one variable first. So you'll get mx dot, then apply the d dt, which is by adding another dot, which is make it acceleration. Okay, so now you need to apply the mechanical module equation, which is this term minus this term. So you get mx double dot minus k x equals to F. Okay, now this seems familiar, right? This is from dynamics course. Dynamics course, okay? As I said, if we have a conservative system, F will be equal to 0. So we'll get mx double dot plus kx equal to 0. You need to understand this part because it's related to dynamics. I'm not sure if it's going to be in your midterm, but just understand it. So we'll get the following: x double dot plus k over m x equal to 0. And as you studied from dynamics, that this term is equal to wn squared. And you can solve this in whatever method that you use, which is differential equations, basically, which is using undetermined coefficient. Anyway, you're not going to use differential equations, but you can see that you can relate this to other courses that you studied before. Okay, so what else we have here? Let's keep it for the last. Okay, there's nothing here. Okay, so we need to understand the polar form of Lagrange Euler or Euler Lagrangian mechanics. You need to obtain or understand some old equations that we used before, some old methods, some old concepts that we studied before. Like, let's say that you want to understand the velocity equation with a rotational motion. Okay, a rotating object that has an angular velocity and radius r. Okay, and that's moving along this path. Right, all right. Find its velocity. You can find the velocity using this equation. V is equal to omega r. Okay. Now we need to apply the variables that we use, which is x and x dot. And you can see that we have a rotational motion. Okay. As for rotational motion, you will get introduced to a new variable, which is theta and theta dot. Okay. X is the displacement. X dot is the velocity. Theta is the angular displacement. And theta dot is equal to angular velocity, which is omega. Okay. Okay, so we need to apply this here. You can get x dot equals to theta dot r. Okay. So this is the introduction of the polar form of Euler Lagrange. Euler Lagrange. Okay, so we need to apply. Let's solve this question. It has a combination between the polar form and the Cartesian, and we'll solve it in two different ways for you to understand the difference between the Cartesian and the polar method. Okay, let's find the summation of kinetic energies. Just a minute, I need to check something. Anyway, so we need to find the kinetic energy. You can see here that we have a rotation. Okay, because the ball is rotating, and we have an elevation, and what else? The elevation, you can see here, it's changing in the inclined surface, and we have a velocity. Okay, we have a velocity. What else we have here? We don't have a spring. Okay, you need to do this. Sorry, you need to do this test every system that you're going to deal with. Check the rotation, the elevation, the velocity, and if there is a presence of a spring. Okay, Since we're going to use rotation, you need to understand the new kinetic energy formula for a rotating object. Previously, we dealt with an object which is moving transitionally, like in a horizontal or a vertical path, or in general any straight path, which was half mv square or half mx dot square. We're going to use a different one for representing the rotational motion, which is half I theta dot square, or you can say half I omega square, but you're going to use this one. Anyway. Okay, now you need to substitute the equations that you're going to use according to these properties that you obtained. The kinetic energy, the first kinetic energy is for the velocity, half mx dot square. As for the rotating object, you get plus half I theta dot square. Okay, I is representing the inertia of the object, the resistance of an object to rotate or to stop in general. Okay, that's the kinetic energy formulas, and there's the, okay, that's a weird sigma, the potential energy, you can say mg, and this elevation here is basically this length with the sine of this angle. Okay, as you see here that I represented the angle with the variable phi. The reason is that we always use theta as an angular displacement and angular velocity in this chapter. So to not get mixed up, you need to use a different variable. Let's say you want to use phi or psi or whatever. Okay, just for you to not to get confused with other variables. For you to understand it in a much conceptual way, you can see that phi is not changing. Phi is not changing. Nothing is changing with the phi. What's changing is the height, which is going to change with the x. Okay? So mgx sine phi. The examiner will not going to be as generous as the equation given here, and it will give you everything here in the system. You need to obtain this by your own knowledge using geometry. Okay, you need to use what you learned from here, from you can say from elementary, not from elementary, from generally in high school or whatever, that you have an angle here and opposite, which is going to be sine phi, and you have a c here, so it's c sine phi, whatever. Okay. Anyway, so you need to understand how to obtain everything that you need to solve the problem. So let's say we need to find the Lagrangian now. The Lagrangian is the kinetic energy minus the potential energy again. Half mx dot square plus half I theta dot square minus jx mgx sine phi. Okay, you see here that we have two variables. Again, sine phi is just a constant. Phi is just a constant. It might be given, it might not be given. Depends on the question. Okay, you see here that we're having two variables here. And you cannot solve the Lagrangian with two variables. So what you're going to do is change the polar to Cartesian, or you can say the other way. So let's start with the Cartesian method. As I said here earlier, like here, yes, here, we need to use these equations to solve that question. Okay, so what we know that theta dot is equal to, not theta dot, x dot is equal to theta dot r. Okay, r is the radius of the ball. Okay, so we need to, you can say, change it. Theta dot is going to be x dot over r. Now substitute it here, you get half mx dot square plus half I x dot over r square plus mg x sine phi. Now we only have one variable in this equation. Now just find the Lagrangian. So get partial L over partial x. It's equal to, this is 0 here, 0 here, so we get to use this one. So you'll get mg sine phi. As for the other part, d dt, partial L over partial x dot, is going to be equal mx double dot for this term. And as for this term, I over r squared, you know there's a square here, I over r squared x double dot. We took the 2, you can say we subtracted the 2 from here and we multiplied by 2. You know how to differentiate, you don't need me here. Okay, then we applied the differentiation with respect of time to get double dot. Okay, now just substitute in the mechanical module, get mx double dot plus I over r squared x double dot minus mg sine phi equals to f. Okay, we solved this problem using the Cartesian method. Okay, let's solve this problem using the polar method. Okay. Again, back to the same equation, the Lagrangian. We're going to use the same Lagrangian. Okay, I just need to copy it. L is equal to half mx dot squared plus half I theta dot squared plus mg x sine phi. Again, we will use the same equations here and just substitute. So we get half m theta dot r squared plus half I theta dot will remain the same squared plus mg theta r, because this is a displacement, not a velocity, sine phi. Okay, now just find the elements of the Euler-Lagrange equation or the mechanical module, call it whatever you want. So partial L over partial theta, you will get mg r sine phi. As for the other part, dt, d over dt, partial L over partial theta dot, you use these. So we get m theta double dot r squared plus I theta double dot. Substitute. Now we get m theta double dot r squared plus I theta dot double dot, sorry, double dot minus mg r sine phi equals, not to f this time, equals to tau or t. Okay, tau or t represent the angular force. You can say there's no angular force. It's not called angular force. It's called torque. Okay, torque. This is the torque of this problem. Okay. Let's solve this problem. There are two methods to solve this problem, but I'm going to use the easiest one. Again, you can see here that we have an angular motion here. Okay, an angular motion here across the same. Of course, it's stopping here, but anyway, just imagine it as if it's a ball or something. And we're going to use the same equations that we used in the previous problem, which is theta equals to x over r, or in the other form, the same thing here, the differentiation with respect of time, theta r. Okay, we're going to use this here. Okay, now let's try to solve this problem. Let me check my notes again. Okay. Do we have a rotation here? A rotation around its axis. Does this object is rotating around its axis? No, it doesn't. Okay, there's no rotation. If it's a ball, yes, it's rotating around its axis, or a pulley, or any other type of systems that rotates, but there's no rotation here. The object is using just a circular path. It's not rotation. Rotation and circular path are not the same, so you need to understand this. Rotation is a type of circular path, but not any circular path can be rotation. Anyway, so let's solve this. What we have here is, I need to just some space. Okay. Okay, you can see here that this object is moving horizontally and vertically, which has this magnitude. Okay, so you can solve it using the magnitude method, or simply use a different method that I'm going to show it to you now. Okay, so this object is moving along, you can say, find the kinetic energy first, and it's moving, so you need to understand that it's moving in a certain path that has the following equation, mx dot square. As I said, if there's movement, there is kinetic energy. Okay, and there is a change in height, which is going to be PE is equal to the change of height. So it's equal to negative mgl 1 minus cosine theta. You need to remember this or obtain it by yourself. It doesn't matter. Okay, now we need to find the Lagrangian. So it's half mx dot squared plus mgl 1 minus cosine theta. Okay, I need you to give a look for this system or this problem. When this object is moving, theta is changing. Okay, and with the change of theta, there is a change of height. So if you want to use the Cartesian variables, it's not a wise choice. It will take more time and it will be hard to derive. So what I recommend is just to use the polar variables or the polar form. So you'll get half m x dot, which is equal to this theta dot squared r squared plus mgl. See, I did a tiny mistake here where I chose r. It's actually l squared. In our case, it's l. Okay, it's l, just l. Okay, mgl squared plus mgl minus 1 cosine theta. Now find the Lagrangian. Partial L over partial theta is equal to, solve this. This is a dot here. Now this doesn't have any theta, so its derivation is going to be equal to 0. And so this one, we have mgl minus mgl cosine theta, right? So derive it, you will get negative mgl. The derivation of cosine theta is negative sine theta. Okay, and there's d over dt partial L over partial theta dot. So again, this term doesn't have any theta dot, so you're not going to use it. We're going to use this one. So we'll get m theta double dot L squared. Now just apply the mechanical module equation, which is m theta double dot L squared, as again this one minus this one, minus mgl sine theta equals to T, torque. Okay, you got this equation. That's called the mechanical module. Okay, let's say that the torque is equal to 0. Again, you're required to solve till this part in the exam. I'm not sure you're going to use the other parts, but just for your information and for your comparison with dynamics. If this is equal to 0, you can see that there is an L can be cancelled. So does M. And remove the L from here. And you will get the following: theta double dot minus G over L sine theta equals to 0. Sine theta, for some reason, I don't know what's the reason, it can be approximated to theta because it's small, but anyway, and you'll get this differential equation. And this part is going to be the natural frequency. Anyway, so you're not going to use all of this. You only needed to obtain this, but just for your information. And you might be asked in the exam, find the angular acceleration. So instead of approximating theta, just take this to the other side. So it becomes double theta G over L sine theta. That's the angular velocity of the whole system. Again, I'm not sure if you're going to use this in the exam, just for your information. Okay, what's left? Okay, finally to the pulley. To understand the pulley problem, or the pulley equation, pulley whatever. Okay. First, you need to understand that there are 4 conditions needed to solve a pulley. The first condition, a massless pulley. This is a massless, as we studied in physics 1, and the rope is inelastic. It doesn't elongate, and there's no slip condition. This one is not slipping. Okay, that's the condition that we studied in physics 1 previously. Okay, so let's solve this. A. Okay, now by looking at the system, you can see that we have the rotation here. We don't have rotation since the pulley is massless. It's not considered because the rotation will give you this equation, half I theta dot squared. And if there's no, if the pulley is massless, then the inertia is equal to 0. Okay, you need to understand this, please. Okay, so the rotation is not going to be considered in part A. We're only going to consider the motion of the 2 masses. Okay, just a minute. Okay. Summation of kinetic energy. You can see that these 2 masses are moving in this vertical path with a certain velocity, which will give you the indication that we have 2 equations that we're going to use. M1 x1 dot square plus half M2 x2 dot square. As for the potential energy, we are going to get negative mg m1g x1 negative m2 g x2. Okay, now apply the Lagrangian. m1 x dot 1 squared plus half m2 x dot 2 squared minus here, so it's going to be positive m1 g x1 plus m2 g x2. Okay, again, we are going to use some different transformation to change the x2 and this equation to x1, or change the x1 to x2, it doesn't matter. So we're going to use something new. Okay, that there's this rope that you used on this pulley. Okay, and there are the masses here. Okay, and these are x1 and x2. x2 and x1. x1, this side of the rope, and x2 is this side of the rope. So the length of the rope is equal to x1 plus x2. Okay? Remember this. Now let's derive the rope to the respective time. A rope to the respective time. You're deriving a constant to the respective time. What's the derivation of this constant? It's going to be equal to 0. So let's say that you have a rope that's 10 meters long. Find its derivation of time, or derivation to the respective time. Going to be equal to 0, right? In this case, yes, it's the same, but we have these. These are not equal to 0. So the derivation of L to the respective time is going to be 0 equal the derivation of x1 to the respective time, it's x1 dot x2 plus x2 dot. This will give you that x1 dot is equal to negative x2 dot. Okay, now remember this and this, because you're going to use it a lot in pulley questions. Okay, now substitute these two here and you'll get half m1 negative x2 dot squared plus half m2 x2 squared plus m1g. Change this. x1 is equal to L minus x2. So mg L minus x2 plus m2g x2. Simplify this, you'll get half m1 x square x2 dot square plus half m2 x2 dot squared plus m1g L minus m1g x2 plus m2g x2. You cannot cancel these terms because m1 is not equal to m2. Okay, now apply the Euler Lagrangian equation. So partial L over partial x2. x2 it's going to be equal to negative m1g plus m2g. You can take g as a common factor, so you get m2 minus m1. We get partial L over partial x2 dot. Get m1 x2 dot plus m2 x2 dot. These terms doesn't have x dot. Now you need to find the derivation with respect of time. So just add the dot here and you'll get these. Again, you can use a common factor, x2 dot m1 plus m2. Okay, now just this term minus this term, get x2 m1 plus m2 minus g m2 minus m1. Okay, now to find the acceleration of this system, this is conservative, rearrange this and you will get that x2 is equal to g m2 minus m1 m1 plus m2. This is going to be familiar from physics 1. Okay, let's say that you're required to find x1 after finding x2. Go back here. You can see here from this relation you can get also x double dot 1 is equal to negative x2 double dot. So x2 here is equal to negative x double dot 1. To find x1, just multiply with negative 1 to get x1. Or just resolve this, but to the respect of x1. Now let's jump into the second case. Okay, or the part B of the question. Part B. If the pulley has a mass, so you can no longer ignore the pulley, but the rope is inelastic and there is no slip condition. Okay, so what you obtain from here that there is a new system here, which is the pulley, the rotation of the pulley, which needs to be calculated and considered. So to solve this part, it's going to be easy, just needs a bit more work. So you have to find the kinetic energy. Again, we have two moving masses with their velocities and everything. We'll get half m1 x1 dots squared plus half m2 x2 dot squared plus half I theta dot squared. That's for the pulley. Okay. Now, as for the potential energy, we get negative mg x1, negative mg x2. The pulley doesn't have a potential energy. Okay, that's just keep it in your mind. Pulley has no potential energy unless the pulley itself is just elevating, but this is going to be very complicated and you're not going to deal with it in your course. Anyway, so you have these two. Find the Lagrangian. It's going to be half m1 x dot squared half m2 x2 dot squared plus half I theta dot squared plus mg x1 plus mg x2. Again, we're going to use these. We're going to use these again. Go down here and try substituting. Now I will use the variable of x1 dot. You can use x2, whatever. Use whatever you like. Half m1 x1 dot squared plus half m2 x1 dot squared. Again, if there's a half here and there's a squared, we cancel it out. Anyway, plus, let's keep this for the last, mg x1 plus mg l minus x1. Okay, Now for the theta dot, how we're going to change it. As I said, we're considering the pulley. Since we're considering the pulley has its own angular velocity and its velocity and everything. But this velocity is connected or related to one of these masses. Now you can assume any mass, but personally I like to assume the mass that's going downwards. By looking to the system, you can see that M1 is just going below M2. It doesn't need to be this case, but you know, that's a personal preference. Assume whatever you want. So I'm assuming, or I'm using, that this pulley is rotating with respect of x1, or x of the mass 1. So we're going to use x theta r, and we're going to x1. So the derivation of time x1 dot theta r theta dot here. Okay, so we're going to use this, change it, theta dot x1 dot over r. Keep this method in mind. So half I x dot r squared. Now find the mechanical module. Partial L over partial x1 dot going to be m1 x double dot. It's okay, dt. Let's solve it one time. Okay, plus m2 x double dot 1 plus I x double dot 1 over r squared. Okay, and partial L over partial x 1 is going to be m1g x1. That's a 1 here. That's a 2. Same thing here, 1, 2. Negative mg. Sorry, there's a mistake here. Okay, I'm deriving and I forgot to derive. Okay, negative m1g and negative m2g. You can take the g as a common factor, m1 minus m2. Okay, now just gather the things up here and you'll get m1 x double dot plus m2 x double dot, it's x1. Just not to get mixed up. I x double dot over r squared minus g m1 minus m2 equals to f. Again, you can solve this using the polar form of Euler Lagrange. You can use whatever method that you want. Okay, I might solve it at the end of the tutorial. I'm not sure. Okay, now let's go to case 3. Case 3 or part C of the question. If the pulley, let me check the recording. If it's working. Okay, the recording is working. All right, cool. Okay, so part C, if the pulley has a mass, the rope is elastic and no slip condition. You can see here that we have a problem here. That just give me a second. As a mass, rope is elastic. Okay, so in part C, elastic and no slip condition. Actually, you have a fifth case, but you can obtain it by yourself. Okay, so we have an inelastic rope, but where there is no slip condition. The meaning of inelastic rope that M1 and M2 and the pulley are not all related. Okay, they're not all related. You're going to have 3 systems. There is Actually, a mistake in the question. Sorry. Part C must be inelastic and slip condition. Okay. What I just said is just for part D. Okay, let's repeat for part C. Sorry. We have an inelastic rope, but with a slip condition. That means that the masses are slipping despite the motion of the other mass. There's a slip. The system is not ideal. This means that what we just solved, the case B, we solved it as all in a one system, that the mass 1 is pulling mass 2 and rotating the pulley. Now there is slip condition. This means that mass 1 and mass 2 might move, but the pulley is not moving. There is a slip, انزلاق. Okay? So this means that we are going to use two mechanical modules, one for the pulley itself and one for the two masses. As the one for the two masses, you can simply solve it in two parts of the paper. The first part is just going to be case 1, massless pulley. Okay, it's going to be case 1 here. Okay, this one. But for the pulley, you need to solve it individually. So get KE is half I theta dot squared. Potential energy is equal to 0. There's no potential energy in the pulley. Remember this. The Lagrangian KE minus PE. So it's going to be half I theta dot squared. So find the mechanical module partial L over partial theta 0 d dt partial L over partial theta dot is equal to I theta double dot. I theta double dot, meaning that the torque is equal to I theta double dot. What you studied before in dynamics, that torque is equal to inertia times the angular velocity, which is the same. Okay, that's for the system. This means that this system has two mechanical modules. Okay, the first one, again, in case 1, it's the same from case 1, this one here. And the second one is that we just obtained here. Okay. Now, let's go to case D. Elastic rope with a slip and a mass pulley that has a mass. This means that the first mass is, I don't want to say it in a concept, but I want you to understand it. This means that M1 can change in height without the change of M2. Let's say that the rope is made of rubber. Okay, if the rope is made of rubber, M2 can change in its height without the need of M1. Okay, you can understand that if you imagine it, and even the pulley can just simply stay still or can move, and it doesn't have to do with the rope, the elastic rope. So this means that you're going to have three systems. The first system is for mass 1, the second system for mass 2, the third system is for the pulley. So going to solve this, as for mass 1, going to need a bigger space. For mass 1, we have a kinetic energy half m x dot squared, potential energy negative m1 here, m1 g x1. As for mass 2, we get a kinetic energy half m2 x dot 2 squared, and the potential energy negative m2 g x2. And for the pulley, for the pulley, kinetic energy is equal to half I theta dot squared. And the potential energy finally is equal to 0. Now find the mechanical module. Okay, so L is equal to half m1 x dot squared plus m1 g x1, and L here is equal to half m2 x2 dot squared plus m2 g x2, and L here is equal to half I theta dot squared. Find the mechanical module, partial L over partial x, and dt, d over dt, partial L over partial x dot. This will give you simply the following: mx1 double dot minus m2 x1, there's no x1, sorry, m2 m1 g equals to f1. Here you'll get m2 x2 double dot minus m2g equals to f2, or the second mechanical module. Here, get torque is equal to I theta double dot. Okay, these are the solutions for this system. Okay, I guess that's it for the first tutorial. So I want to keep it simple. I guess so. Yes, that's it. We're going, in the next tutorial, we're going to solve some new type of questions based on the stuff that you studied or that you understood from this tutorial. Okay. Again, revise this tutorial, solve the same questions. We're going to solve new questions on Sunday. If you want to view these questions, I sent you the problem set in your email. So just please view them. Mainly, there are going to be 4 problems. If you want to take a screenshot, it's here. These are the 4 systems that you're going to use to solve in the next tutorial. Okay. Just a pulley, normal pulley system. This one the same here. This one pulley with a spring. This is a spring with a disc. And this one inclined surface with a spring. It seems complicated, but these 4 problems that are going to make you appreciate Euler Lagrange over the Newton method. Okay. Do you guys have any question?
يعطيك العافية.
Okay, guys, yeah, you can leave. I will upload the recording here on MS Teams. And good luck. You can contact me if you need anything in WhatsApp or something. All right. Good luck, guys.
تمام، مشكور.
Bye bye.